some function z equals f of xy. I'm going to make it be some unknown constant c times x squared times y. I want to use this function and find the value of c so that f is what's called a probability density function over a certain domain. D is the set of all points x, y. Say x goes between 0 and 2, and y goes between 0 and 3. So the domain is a rectangle shape, looking about like that. That's the domain. Probability density functions for short are called PDFs. What do you use probability density functions? You use them to find probabilities. How? By integrating them. How do you do this problem? How do you find this value c? You want the integral over the entire domain to equal 1, which represents a probability of 1 or 100% chance. For sure, 100% chance x and y are going to satisfy these two conditions over this domain. We want this to integrate to 1. But what do I mean in this function of two variables to integrate to 1? I mean, I want its double integral to equal 1. I want the so-called double integral involving two integral signs of this function to equal 1. Leave a little space like that. When you're thinking about a double integral in the abstract, you put the region of integration down here. And instead of putting dx or dy here, initially you put dA. What's going on here intuitively? Intuitively, let's draw the positive x-axis going this way, positive y-axis going into the screen like this. Intuitively, I want the volume, not the area, but the volume under F to equal 1. This is the volume under the graph of z equals f of xy over this domain D. So the domain D in this 3D picture is this sort of slanted rectangle going into the screen. The graph of F is some kind of surface above that domain. The integral represents the volume of the solid under that surface. And to be a valid probability density function, to be a valid model, you want that volume to be 1. Double integrals, they give you volumes instead of areas. Or sign volumes, possibly negative, meaning if the graph goes below the xy plane. If the graph is entirely below it, the double integral is going to give you a negative volume. The opposite of the volume above the graph and below the xy plane. Intuitively, you could think of this expression here, f of xy dA, as a volume element, dV. You could think of dA as a tiny little piece of area right there. Infinitesimally small, maybe. Think of f of xy as being a height, and then the product, so to speak, as being a height times base, a volume of an infinitesimally thin rod under this graph. And when you write the integrals, you're imagining adding up all those volumes to get the total volume under the surface. Is that rigorous? No, it's intuitive. I'm not proving anything. I'm trying to describe intuition, how people think about these things. This can be approximated, as you might expect, with Riemann sums. Somehow in higher dimension, a higher dimensional version of that. But what we do instead, most typically, is we avoid Riemann sums when we can. We like things to work out not so messy. We try to actually do the integral by representing it as what's called an iterated integral. Computational technique. Write the double integral over D as an iterated integral, where you're doing single integrals twice. That's what iterated integral means. Do single integrals twice. A first time, an inner integral, and then a second time, an outer integral. When the domain is a rectangle, the iterated integrals are pretty easy. For this example, we're doing a double integral over D of c times x squared times y. We do replace the dA with what you might guess, dx dy, or the other way around, dy dx. And you do have ordinary limits of integration for these individual integrals. And there is an inner integral, which gets done first, and an outer integral, which gets done second. For emphasis, I will use parentheses. Let's do it. Let's use dA equals dx dy. Again, I could also do it as dy dx. Let's do it dx dy. So the integral is going to be with respect to x, because the dx comes first. And the outer integral is going to be with respect to y, because the y comes second here. The outer integral y, look at the picture, goes from 0 to 3. Let me use parentheses here. The inner integral, x, goes from 0 to 2. The inner integral is done with respect to x. The outer integral is done with respect to y. I am writing parentheses, like you see here, to emphasize there's an inner integral and an outer integral. However, most of the time, most people don't bother drawing parentheses. They just realize in their minds there's an inner integral and an outer integral. And you just do it step by step, kind of analogous to doing partial derivatives. If I were to differentiate this with respect to x, I treat the y as a constant. Now I'm integrating with respect to x. I'll treat the y as a constant still. I'll factor the c itself out in front of the integral. You might expect you can do that, and you can. Treat the y as a constant. I'm integrating with respect to x. Get x cubed over 3. Treat the y as a constant. X goes from 0 to 2 because for the inner integral, it was with respect to x. Plug in x equals 2, get 8/3 y. Plug in x equals 0, get 0 y, which of course is 0. We're almost done. We got c times the integral from 0 to 3 of 8/3 y. It's going to be an easy thing to finish it. We're going to get c times, if I integrate 8/3 y with respect to y, I get a y squared. I also divide by 2. I get a 4/3 y squared. Y goes from 0 to 3. 3 squared is 9. 9 times 4/3 will be 12. Plug in 0, get 0. So I get 12c. To solve for c, I set this equal to 1. And solve for c. That implies c is 1/12. That's the answer to the question. In order, you want the integral to be 1 for this to be a valid probability density function. That doesn't mean that integrals, double integrals, are always equal to 1. I'm choosing c so that the double integral equals 1. So the PDF is Z equals f of x, y. C is 1/12. 1/12 x squared y over d. It is important to specify the domain. X is between 0 and 2, y is between 0 and 3. Conceptually, realize that when I do that inner integral with respect to x, I still get something that involves y. It's still a function of y. That can happen in general. That will happen in general. Doing this in Mathematica, you don't need parentheses. You can just put two integral signs. Let's check this calculation. Y goes from 0 to 3. Tab over to the next box. Press the integral button again. X goes from 0 to 2. C was 1/12. Dx dy, 1. I hope it makes good intuitive sense that I could do this in the other order. Why do a dx dy? Why not do dy dx? If I do that, though, I need to change the limits of integration for the outer integrals around. The details of the hand calculation will be different, but the final answer will be the same. What gets harder is doing these things over non-rectangular domains. Triangular domains, for example. Oh, let's make it kind of tricky to end class today. Let's say it's a triangle that looks like this. Let's say this is 4 and this is 5. This is 2 and this is 5. Let's say that's our domain. This is our D. And I'd once again like to take this function, f of xy equals c times x squared times y, and make it a probability density function, a PDF, over this domain. But now the domain is not a rectangle, it's this triangle. And C could be different, probably will be different, to make the total volume of the graph, under the graph, and above D equal to 1. I'll probably get a different C. Conceptually, you're still wanting to choose C so that the double integral still equals 1. Still want this to be true. But the way you do that, the details of how to do that with iterated integrals gets harder. You might even say a good deal harder, trickier. It is important to identify the boundaries, equations for the boundary here. This line, for example, is a line through the origin with a slope of 1/2. It's y equals x over 2, which is equivalent to x equals 2y. This one would have equation y equals, let's see, what would the slope be? 3. 3 times x minus 4 plus 2, which simplifies to 3x minus 10. Or equivalently, x equals y plus 10 over 3. Doing some algebra pretty quickly in my head here. 1/3 y plus 10/3. And this one's going to be y equals x right there. That's important. Another important thing is to, especially with a shape like this, break it up into pieces. For example, like this, where on each piece, D is a region between two graphs. That's one way to do it, the simplest way to do it. Do the integral over each piece individually and then add the results. Hope that makes some intuitive sense that you would do that. Maybe I'll call this piece D1 and this piece D2. The integral over D is going to be the sum of the integrals over D1 and D2. Let's now do each of those integrals as an iterated integral, and I won't bother writing parentheses. Is it going to be easier to do dx dy or dy dx? If I break it up like this, it's best to actually do dy dx. When you've got the region as being between two functions of x, in both cases, it's best to do dy dx. We could break it up another way. We could break it up with a horizontal line like this and think of it as regions between two graphs of two functions of y instead. And you do want to have the flexibility to do such things. In that case, you would do dx dy. In this case, we want to do dy dx. The outer integral is going to be with respect to x. Over d1, notice x goes between 0 and 4. And y does not go between two numbers, but instead goes between two functions of x, x over 2 and x. For the inner integral, the limits of integration depend on x. And this is another big point of emphasis in section 13.1. Is doing things like this, where your limits of integration depend on variables. Cx squared y, we're doing dy dx. For the other integral, we do something similar. Look at the picture again. Over d2, x is going between 4 and 5. So the outer integral goes from 4 to 5. The inner integral does not go from x over 2 to x, but instead from 3x minus 10 to x. Weird but true. 3x minus 10 to x. Cx squared y dy dx. I could certainly do this by hand, but I'm running out of time. Let's try to imagine doing this integral by hand. I'd be integrating with respect to y. I treat the x like a constant. If I integrate cx squared y with respect to y, I'll get a y squared over 2. C over 2, x squared, y squared. Something similar will happen here. But then I've got limits of integration that depend on x. When I evaluate that, I'll go from y equals x over 2 to y equals x. I will replace the y with x over 2 and x. You'll be doing squaring and you'll be doing a subtraction as well by the fundamental theorem of calculus when you do that. Don't have time to do that by hand. Let's have Mathematica do this to finish. So I'm just going to type in what you see there by hand. 0 to 4, tab over here, hit the integral button again. X over 2 to x. Yes, that is okay. C times x squared times y, dy dx. Then add a similar integral. I'll copy and paste. X goes from 4 to 5 now. Y goes from 3x minus 10. Correct, right? 3x minus 10 to x. When I enter this all, I'm going to get a number times c. 881 over 6 times c. In other words, to make it a PDF, c needs to be 6 over 881. If I set c equal to that and re-enter this, the answer will be 1. It's a valid PDF over this triangular domain.